Hello everyone, this is Sarvesh, lecturer in Civil Engineering, Government Polytechnic, Station Control. The course is Reinforced Concrete Structures. In lecture 4, it is a continuation to the previous lecture on design of T-beams by limit state method as per IS 456-2000. After completion of this lecture, you are able to know how to determine the moment of resistance of T-beams based upon the given data, and you are able to understand the provisions of transverse reinforcement, and we will solve some example problems for determination of effective width of the flange, and what are the different types of problems in T-beams, and we'll discuss about the procedure how to solve the problems on analysis of T-beams, and we'll solve some example problems. So before going to start today's lecture, just I would like to recap whatever we were discussed in the last class. So in last class, we have discussed about the what is meant by metal axis, moment of resistance, and how to determine the moment of resistance in T-beams. Also, we were discussed about the moment of resistance for different depth of metal axis, because the moment of resistance is depends upon the depth of metal axis in T-beams. So the depth of metal axis in T-beams are different types. That is the depth of metal axis within the flange and depth of metal axis within the web. Right. So the procedure to determine the moment of resistance for the T-beam when the depth of metal axis within the flange is different as compared to the uh, metal axis lies within the web. So the procedures we were discussed in last class. So today we are going to discuss about the first, before going to the procedure, just I would like to discuss about the transverse reinforcement, which is required to provide the in T-beams as per IS 456-2000 class 23.1.1b. As per this class, the transverse reinforcement should be provided at the top of slab when the main reinforcement of the slab is parallel to the beam, right? Then such reinforcement should not be less than 60% of the main reinforcement. This is very, very important. 60% of the main reinforcement at the mid span of the slabs. That means the transverse reinforcement should be provided at the top of the slab when main reinforcement of the slab is parallel to the beam, and that reinforcement should not be less than 60% of the main reinforcement at the mid-span. This is a transverse reinforcement you need to provide in the slabs. And this is a beam, and this is the another beam. If you cut the section and if you see it, so this is the reinforcement provided, and this is the attachment. So this is the distance of this one is 0.2 greater than or equal to 0.25 this is also should be greater than or equal to 0.25 L, and this is PW, that is width of the beam. And just we'll solve one example problem on determination of the effective width of the plan. So in last class, we were discussed about what is meant by effective width of the plan and actual width of the plans, and how to determine this for homogeneous and isolated sections for L section and TV. So for better understanding, we'll solve an example problem on determination of effective width of the plan. So here the problem is to find the effective width of following simply supported beam of effective span 5 meters, and the center to center distance of adjacent panels is 3 meters, and the width of the web is 230 mm and thickness of slab is 120 mm. So for this, you just write down the given data. So given data is whatever the length is given, L is equal to 5 meters, width of the beam is 230, and BF, that is thickness of slab is 120 mm. And here the beam is simply supported, therefore the distance between the zero movement, the points of zero movement, that is L not equal to L equal to 5 meters. So how to determine this effective width of the plant? The effective width of the plant is nothing but the center to center distance of the adjacent panels minus BW will get 2770. That means this is suppose this is the middle of the my text TV, right? And this is uh, L naught is nothing but the distance between the sorry, not, yeah, the adjacent center to center distance of adjacent panels is 3 meters. That means from this center to this center. This is called your 3 meters. Therefore, the width of the flange is the center to center distance minus width of the field. That is what? That is 27, right? So next is effective width of the flange is nothing but is the least of the following. That is, one is DF is equal to, that is effective width of the flange equal to L naught by 6 plus BW plus 6 into DF. And if you substitute the values, that is 5000 by 6 plus 230 plus 6 into 120, you get 1783.3 mm. And similarly, BF is equal to DF plus, that is BW, that is this one, plus half of this clear distance plus half of this clear distance, that is 230 plus 277 by 2 plus 277 by 2, you will get 3000. So out of these, as per codal provision, we need to take the least of, right? So the list of these two is 1780. This is the effective width of the plant of a given section, right? So like this, you have to determine the effective width of the plant based upon the given data. So in T-beams, there are two types of problems. One is analysis problems, that means determination of moment of resistance for the given T-beam based upon the given data. And another one is to determine the safe load or ultimate load that the beam can carry based upon the given properties or given data. That is one type of problem that is called as analysis problem. And another one is design problem. That means we need to design the beam. So this is design means you need to start from starting. That means assuming the dimensions of the section and effective span calculations. Then check for depth. So all these data are same as your rectangular beam, but there are some different based upon the depth of it. So that problem is called as design problem. So both will discuss, uh, right. So first we will discuss about the design problem. So the procedure of design problems. So based upon the problem, you just list out the what is the given data. That means the width of the flange, width of web, depth of the flange, or thickness of the slab, effective depth of the beam, area of steel, and characteristic strength of concrete and steel. And required is you need to calculate the moment of resistance. So for this, how to determine this moment of resistance? So first step is assume, because see here you need to determine the moment of resistance. To determine the moment of resistance, you need to know the depth of neutral axis. So here, the depth of neutral axis is classified into two types. Suppose this is a T. So first, before starting, you need to determine the depth of neutral axis. But here, the problem is it is whether it is within the flange or whether it is within the web. That you need to determine, right? So because if you know whether it is whether the depth of neutral axis is within the flange or within the web, then only you are able to determine the moment of resistance. Because the concept of determining the moment of resistance in T beams is different for different if the depth of neutral axis is within the flange and different for the depth of neutral axis is within the web. So how to determine for different cases we were discussed in our last class, right? So therefore, first you have to find out whether the neutral axis is within the flange or within the web, right? So, but before starting, we don't know whether it is within the flange or within the web. So for that, you need to assume. The first step is assume that whether it is within the flange or within the web. You can assume any situation and calculate the XU. Then that XU should be compared with your thickness of slab, that is DF, right? If XU is uh, less than DF, then it is the neutral axis within the flange. If XU is greater than DF, then the neutral axis is within the web, right? Yeah, so for the simplicity, I'm assuming here the depth of neutral axis is within the flange, right? So if the depth of neutral axis is within the flange, and to determine the depth of neutral axis, so you need to equate the compression force equal to tension force. That means compression force is 0.36 FCK PF XU equal to 0.87 F of I into A of S, right? So from this equation, you can determine the XU value, that is 0.87 F of I into A of ST by 0.36 FCK into VF, where VF is the width of the flange. This is your V of F, right? And check whether your assumption is correct or wrong. if XU is less than DF, where DF is the thickness of slab. This is called DF. If your XU is less than or equal to DF, then our assumption is right. That means the depth of neutral axis is within the flange. Right? If XU is greater than DF, then the neutral axis is not within the flange. That means our assumption is wrong. Right? So the depth of neutral axis is within the web. So then you need to again determine the depth of neutral axis based upon this criteria. Because if the criteria changes, the formula will change for determination of x. Right? Suppose, for example, if xu is less than df, therefore our assumption is right. Therefore, how to determine the moment of resistance for this case? So after determining this one, let us assume for the first case, if the depth of neutral axis is, we are assuming it is within the flange, then we got our assumption is right. If our assumption is right, then you need to calculate the XU max as per AS 456 2000 with XU max by D values based upon the grade of concrete and T. Right? Then compare with the XU equal to XU max. That means if XU is so if XU is less than XU max, then it is called as under reinforced section, and XU is equal to XU max is balanced section, and XU is greater than XU max is called as over reinforced section, right? So if it is a over reinforced, if it is a under reinforced or balanced section, so directly if it is a um, under reinforced section and balanced section, you can determine the moment of resistance by using these formulas. That is, Nu is equal to 0.87 f of I into AST to D minus 0.42 XT, or you can use this formula, that is 0.36 FCK BF XT into D minus 0.42 XT. Any of the formula you can use and determine the moment of resistance if it is XU less than XU max and XU is equal to XU max. Suppose, for example, if you got XU is greater than XU max, that means over reinforced section. So in that case, as we discussed in the previous classes, that means the limit state method as per IS 456,000, we have to avoid the over reinforced section because of sudden failures, right? So therefore, you just restrict your XU equal to XU max. That means, so if this is the case, then your XU is equal to XU max. So use same equations for determining the moment of resistance by replacing XU is equal to X, right? If it is a over reinforced section, that is very important. To just you should remember this criteria also, right? So all these things are valid if the depth of neutral axis is within the flange, right? Now coming to the another case, that is if the depth of neutral axis is within the web, that means this is the case. If the depth of neutral axis is greater than x max. So as we discussed earlier, if the x is greater than df, that means the neutral axis is in the flange. Again, there are two cases in this case. That means the case one is if x is greater than df, there are two cases. That is df by D is less than 0.2 and df by d is greater than 0.2. What it represents? That means if df by d is less than or equal to zero point 0.2, the stress within the flange is uniform, right? That means the rectangular portion is uniform. If df by d is greater than zero point 0.2, then the stress distribution along the thickness of the flange is not uniform. It is a combination of parabola and rectangular, right? So therefore, in second case, it is very difficult to determine the compressive forces. Therefore, as per IS 456-2000, it is suggested that you need to uh, modify the thickness of flange from DF to YF, right? So how to modify we'll discuss. So suppose here the case is the depth of neutral axis is within the flange and the criteria is DF by D is less than or equal to 0.2. So if this is the case, then for the concept we were already discussed this earlier, how to determine the moment of resistance. So if this is the case, then you need to determine the uh, depth of neutral axis by equating the compression force equal to tension force. So for this case, the compression force is divided into two parts. The compression force taken by the flanges and the compression force taken by the bed. So just I have already detailed explanation have been done in our previous lecture. So if this is the case, right? So the compression force taken by the flanges is 2 and web that you need to calculate separately and you will add it, you will get the total compressive force. So the compressive force taken by the web, suppose this is your neutral axis XU. Therefore, the compressive force taken by the web is 0.36 FCK W into XU. This is the compressive force taken by the flange, the web, and the compressive force taken by the webs is nothing but the 0.45 FCK into BF minus BW into DF. That is equal to the total tension force, that is 0.87 per 5 into F S, right? So therefore, after determining the XC value, that is depth of neutral axis, again you need to determine the XC max, that is the maximum depth of neutral axis. So after that, just use the moment of resistance can be calculated by using this equation. That is 0.36 FCK BW into XU into D minus 0.42 XU plus 0.45 FCK DF minus DW into DF plus D minus 0.5 into DF. So from this equation, you can determine the moment of resistance if the depth of neutral axis is interval and df by d is less than or equal to 0.2, right? Right. So, this is the calculation of moment of resistance for the depth of neutral axis within the web and df by d is less than or equal to 0.2, right? And next case is if the depth of neutral axis is within the web, right? And if the df by d is greater than 0.2. As I said, if this is the case, that means if the depth of neutral axis is within the web and df by d is greater than 0.2. What it represents? It represents that if the df by d is greater than 0.2, therefore the stress distribution within the flange, thickness of flange is not uniform, or I can say that it is the combination of rectangle and parabola, right? But not exactly. It is it's just like just I would like to write it right. So within the rectangle, it is seems to be like this. So somewhere else, the rectangular portion will touch us here. So this is the width of plan somewhere. So up to here it is constant. After that, it is very difficult to determine the average stress of this one. So that is why, as per IS 450 it is suggested that you need to modify the thickness of plants as per IS 456 2000 instead of DF. So that modified thickness is nothing but your YF. Yeah. This is the modified thickness of plants. That means it is assuming that within this modified thickness, the stress is uniform, right? So by using this modified thickness, you can use the you can determine the moment of resistance of the section, right? So, how to determine this modified thickness? This modified thickness is calculated by using this formula. This is suggested by the IS 456 2000. That is 0.15 x2 plus 0.65 df, and in no case it should not be greater than df value. And therefore, based upon this equation, you can find out the uh, depth of neutral axis again. And how to determine? As usual, the depth of neutral axis can be determined by equating the compression force equal to tension force. So here, the compression force. So after calculation, the effective that is modified thickness of plant, then it is similar to your second case. That is depth of neutral axis is in a way, and df by d is less than or equal to 0.2. But only thing is, instead of using df, you have to use the yf. See here. So here we are equating the compression force equal to tension force, right? So compression force is same as it is the compression force taken by the web and the compression force taken by the plant with modified thickness of plant. That is 0.36 FCK BW XU plus 0.45 FCK B of F minus BW into YF is equal to tension force. That is 0.87 F of 0.8. And YF should be calculated from this form, right? And see here, the one thing you can observe it, see the XU is also unknown and YF is also unknown. Two unknowns, right? But here, from this equation, write down your YF, you just substitute this whole equation at here, therefore the unknown is only XU. So you can find out the XU value. So after getting the XU value from this equation, then find out the YF, right? So after that, you just calculate the depth of actual depth, maximum depth of neutral axis as per IS 456 2000, right? So then compare whether it is XC is greater than less than XC max or not. If it is less than, you can determine the moment of resistance by equating from this formula, that is 0.36 xk B XU into D minus 0.42 XU plus 0.45 FCK into D of F minus BW into YF into D minus 0.5 Y of F, right? And if XU is greater than XU max, then because as per IS 456 to 2000, you have to avoid the over reinforced sections, right? So then, sorry, you just restrict your depth of neutral axis instead of XU equal to XU max, right? Then use the same equation by replacing X equal to X max and find out the depth of, moment of resistance. So this is how you need to determine the moment of resistance for all these three cases. right? Yeah, just now I told you, if XU is greater than XU max, then restrict your depth of neutral axis to XU max, then determine the moment of resistance by replacing your X equal to XU max, that is 0.36 FCK BW XU max into D minus 0.42 X plus 0.45 FCK into B of F minus BW Y of to D minus 0.45 into Y of F. Right. So this is how you can calculate the moment of resistance for different cases. So just we'll solve an example problem for determining the moment of resistance as the analysis problem, right? So this is the problem that is calculate the moment of resistance of a TV with the following data. That is width of the flange is 800 mm, thickness of flange is 110, width of web is 600 mm, area of tension reinforcement is 2500 mm square, FCK is 20 Newton per mm square and F of Y is 415 Newton per mm square. So as we discussed, first write down the given data, and after that determine the uh, depth of neutral axis. So as I told that, so before starting the problem, we don't know where the depth of neutral axis is placed. So for that, first assume the depth of neutral axis is within the flange or within the web, and accordingly you can use the corresponding formula to determine the depth of neutral axis. So here I am assuming that the depth of neutral axis is within the flange. Within the flange. So equating compression force equal to tension force, that is 0.36 HKBF is equal to 0.87 F of into Fest. So from this I can find out the XQ is equal to 0.87 F of into AST by 0.36 HK to BF. So from this equation, if you substitute the values, the XU is equal to 156.7 mm. Right? So this is the depth of neutral axis. Then next step is you need to check whether it is our assumption is right or wrong. How to check? By comparing with the thickness of the flange. What is the thickness of the flange? So before that, I would like to write out just for the T section for a this is your T section, and so width of flange, yeah, this is the width of flange 800. Thickness of flange, this is thickness of flange. Width of web, yeah, this one is the width of web, and area of series here, right? Anything else? So our width of flange is 110 mm and XU is 156 mm. So that means it is greater than the DF. So what it represents? So our assumption is wrong because the depth of neutral axis is 156 mm and the thickness of flange is only 110 mm. So that means XU is greater than DF. That means our assumption is wrong. What we were assumed? We assume that the neutral axis is within the flange, but it is not correct. What is correct? The depth of neutral axis is within the web. So therefore, if the depth of neutral axis is within the web, so there are two cases again, because whether the stress distribution is constant within the thickness of flange or not, that is also we need to determine, right? So how can you determine that? Based on the df by d value, right? So sorry, here the d effective depth is 600. That is not the of right. So Here df by d is how much? 110 by 100. This is less than or equal to 0.2. That means within the thickness of flange, the stress is constant distribution. So therefore, so this is the actual diagram. I think I have to put it in starting, right? So these are the dimensions of the number. This is 800, this is 110, this is 82, this is 600, and the effect to the and width of the beam is 300, right? Okay. Right. So after determining that if the uh, depth of neutral axis is between the web and df by d is less than or equal to 0.2. Therefore, we need to determine the compressive depth of neutral axis by using the different equation. That is, if this is the case, you need to determine the compressive force taken by the flanges plus compressive force taken by the web is equal to tension force. So from this equation, this is the compression force taken by the web, that is 0.36 FCK into BW into XU, and plus the compressive force taken by the flange, that is 0.45 FCK BA of F minus BW into DF, that is equal to 0.87 of into AS. And here, if you substitute the values, that is 0.36 into 20 into 300 into XU plus 0.45 into 415 into 800 minus 300 into 110 is equal to 0.87 into 415 into 2500. If you solve this equation, because everything is known except XU, so then you can solve this equation and you will get the XU value, that is 188.7. And remember, this value should be greater than the thickness of flange. So that is for your cross checking, right? Then after getting the XC value, then you need to determine the XC max as per the IS 456 2000. That is as per the codal provision. If the grade of steel is 415, therefore the XC max is equal to 0.48 T, where T is the effective depth of the TB, that is 600. If you substitute the values, that is 0.48 into 600, we get 288. So our actual depth of neutral axis is 188 mm, and the maximum depth of neutral axis is 288 mm. So therefore, it is a XU is less than max. That means it is under reinforced section, right? Where if XU is less than XU max, it is classified as under reinforced section, right? So therefore, you can determine the moment of resistance. So that is 0.36 FCK VW into XU into D minus 0.42 XU plus 0.45 into FCK into V of F minus PW into DF into D minus 0.5 into DF. That means it is nothing but compressive force into lever arm. But here we have two compressive forces, right? As I told now, don't confuse it. It's similar to our rectangular beams for determining the moment of resistance. So the only thing is here I am dividing into two parts. That is the compressive force taken by these flanges and compressive force taken by this web. So for this one, the moment of resistance due to the compressive force taken by the flange is The compression force is 0.45 stick into V of F into BW into DF, that is the compressive force. And lever arm is, suppose this is your tension reinforcement, from here to center of this flange, that is D minus DF by 2, that is 0.5 DF. And similarly, this is D minus 0.42 XD, right? So if you substitute the values in this equation, that is 0.36 into 20 into 300 into 188.72 into 600 minus 0.42 into 188.72 plus 0.45 into 20 into 800 minus 300 into 110 into 600 minus 110 by 2. So if you solve this equation, you will get the moment of resistance of the given section. Here we got it as 480.05 into 10 power 6 Newton m. So this will become as 482.05 kilonewton meter. Right. So this is how you need to determine the moment of resistance of a given section. Right. So for this, I would like to conclude the session. So just summarizing what we were discussed till now. So till now, first we were discussed about the transverse reinforcement. That means the provisions of IS 456-2000 for determining the transverse reinforcement in beams. Then we have discussed about the uh, we have solved some problems on determining the effective width of the flange. That means in last class we have discussed what is meant by effective width of the flange, because see, the stress distribution is minimum at the edges and maximum at the center. So for simplification, we are assuming that assuming as a rectangular distribution, and by reducing the actual width of the flange. So based upon the IS 456-2000 and based upon the given data, you need to determine the effective width of the flange. So we have solved one example problem on determination of effective width of the flange for T section. So later, we have discussed about what are the different type of problems arises in T-beams. That means analysis problems. That means based upon the given data, you need to determine the moment of resistance, or you need to determine the maximum load that the beam can carry, whether it is a safe load or ultimate load. Right. Another type of problems are design problems. Right. So today we have discussed about the procedure for analysis problems. That means determination of moment of resistance, or determination of maximum load that the beam can carry. So in that procedure, first we have to assume, because before starting we don't know whether the depth of neutral axis is within the flange or within the web, right? So first we need to assume that the depth of neutral axis is in the flange, or you can assume whether it is in depth of neutral axis within the web also, right? So but easiest way is we can assume the depth of neutral axis is within the flange, then determine the depth of neutral axis by equating the compression force to tension force, and then you can compare whether your assumption is right or wrong. That can be determined by comparing your determined x2 with respect to thickness of flange. If xu is less than df, df is nothing but your thickness of flange, then our assumption is right. That means the depth of neutral axis is within the flange, right? If the if the XU is greater than DF, then our assumption is wrong. That means the depth of neutral axis is within the well, right? So in first case, if the depth of our assumption is right, that means if the depth of neutral axis is less than the DF, then again you determine the XT max based upon the grade of scale, right? Then compare it, and if it is X is less than or equal to X max, then use the bending moment equations whatever we were discussing. If XU is greater than X max, then you need to restrict your XU equal to X max, right, to avoid the sudden failures. Then you can use the same equation by replacing X equal to X max for determining the moment of resistance, right? And similarly, if the depth of neutral axis is within the web, the two cases will arise. That is, whether the stress distribution is uniform within the thickness of flange or not. That can be determined by the ratio of df by d, that is effective depth small d. If df by d is less than or equal to 0.2, therefore the effective stress distribution is uh, constant within the thickness of flange. If df by d is greater than 0.2, then it is not uniform. So if df by d is less than or equal to 0.2, right, then you can determine the depth of neutral axis by equating compression force to tension force. By that means the compression force is nothing but the compression force taken by the flanges and the compression force taken by the bed separately, and equate compression force to tension force and determine the depth of neutral axis. And again, you just compare with your X max, right? If it is less than or equal to X max, then use the calculated moment of resistance based upon the formulas, right? If it is greater than X max, then you need to restrict your X equal to X max and replace same values, X values with respect to X max, then determine the moment of resistance. This is the if df by d is less than or equal to 0. If df by d is greater than 0.2, then you need to determine the uh, modify the thickness of flange as per IS 456-2000, that is y of f. Then due to that modified thickness, then again you need to determine the depth of neutral axis, right? And for that depth of neutral axis, again you need to check with XU with respect to X max and determine the moment of resistance based upon the equation whatever we have discussed. And this is the all our procedure. And later we have solved an example problem to determine the moment of resistance. And we have solved the problem, and in the problem we got X is greater than df, that means the neutral axis is within the web, and df by d is less than or equal to 1. So that means the stress is uniform with the thickness of web, sorry, flange, right? So accordingly we have used the formulas, and we were determining the depth of neutral axis and moment of resistance of the given section. Right. So for this, I will have to conclude this lecture, and next class we will discuss another topic. So thank you very much.